In this example, we are asked to evaluate the integral from 0 to 1 of 4 over 1 plus t squared j plus 2t over 1 plus t squared k dt. Now, there are a few ways of thinking about this. Let me start with some steps that we would not ordinarily write. I just want to basically show you how we can use things we already know about integrals and other properties to make this more approachable. By any reasonable definition of an integral, a sum of terms in an integrand, we can restructure that so that the integral becomes a sum of integrals of the individual terms, right? So we see this plus here for these two pieces. So we should be able to break this up as the integral from 0 to 1 of 4 over 1 plus t squared j dt plus the integral from 0 to 1 of 2t over 1 plus t squared k dt, right? Not worrying about the fact that j and k are vectors, just thinking about them as being constant quantities. We can split up this integral like this. And again, thinking about these as being constants, you know that whenever you have a constant, you can pull that out front, right? So we could write this as j times the integral from 0 to 1 of 4 over 1 plus t squared dt plus k times the integral from 0 to 1 of 2t over 1 plus t squared dt. Now this is how we would usually write things if j and k were ordinary constants. But, you know, they're not. They're unit vectors. So we usually think of those as being, you know, we like to have the component first and then the unit vector. So if you really want to do that, you could rearrange this, and putting this in parentheses now, we could say we have the integral from 0 to 1 of 4 over 1 plus t squared dt. That quantity, which, looking at what's in the parentheses here, you see this is just a scalar, right? There is no vector business here. This is just a Calc 1 style problem. But that is times j. And then we have the integral from 0 to 1 of 2t over 1 plus t squared dt. Again, another Calc 1 style integral here, times k. All right. Now again, these first couple lines here, I'll just kind of do this. We would not normally write these. I was just trying to show you some step-by-step manipulations of how we get to this form. This form is how the textbook expresses integrals of vectors. And once we've done that, of course, we can evaluate each integral individually and work that out accordingly, right? So we have, hopefully you recognize these, 4 is a constant, 1 over 1 plus t squared integrates to an arctangent. So I was about to write out arctangent, but it's shorter to write it this way. So we have the inverse tangent, or the arctangent, of t, and we want to evaluate that from 0 to 1, j, plus, let's see here, we have, if we do a u substitution of 1 plus t squared, the derivative is 2t, so there is our, the 2t dt would be du. So we have something of the form 1 over u that we're integrating. So that would give us the natural log of the absolute value of 1 plus t squared. And that is being evaluated from 0 to 1 also, times k. So we have 4 times, let's see, arctangent of 1 would give us what? Pi over 4 minus the arctangent of 0. We have the natural log of plugging in 1 here, we get 2, minus the natural log of plugging in 0, we have 1, times k. Pi over 4 minus 0 is, of course, pi over 4. The 4's cancel, so it looks like we have pi j plus Natural log of 1, remember, is 0. So we have log 2 times k. So there we go. This integral here from 0 to 1 of all of that junk dt works out and simplifies to pi j plus the natural log of 2k. Which, if you wanted to use the component form, remember, of course, you could always write that. Be careful of which things we have here. Even though we only have two non-zero terms, these are j and k, which means we're working in a three-dimensional setting. So you could also write this answer as 0 pi natural log of 2. That would be another way of expressing this if you prefer. Both of those are fine. So that's the idea. Integration is just done component-wise. You just keep track of everything, keep the components separate. Again, these first couple steps, you don't want to write those. That was just me showing kind of what's going on. If you want to write anything, you could go to this one, or you could kind of dive right in and start working on these things. If you do write it in a fashion like this right here, where we have these two integrals in parentheses, that would be a convenient time, particularly if the integrals are messier, if you're not sure that you can do those easily in one step, or if you simply find that this is much too cumbersome. From a step like this, you could easily just come off to the side, basically, or interrupt your work, however you want to do it, and just take maybe that first integral. Say, okay, well, the integral from 0 to 1 of 4 over 1 plus t squared dt, and then start doing your work, and however many steps it takes you to get that and figure out that it's pi. And then you can say, okay, now let's look at this integral, and you can work out that integral, and then you just have less to write at once. You can work that out, simplify it down to natural log of 2, and then at the end you can bring those back and say, so, and say the original integral is this, and you can just stick those back together at the end. So if you find it cumbersome to write all of this out together like this in these pieces, then, you don't have to. That's okay. Alternatively, if you want to take this all in a chunk, you could take an integral like this and say, okay, well, we have this thing to integrate. That thing is going to be, we get 4 arctangent of t times j plus the natural log of the absolute value of 1 plus t squared times k, evaluated from 0 to 1. Like, you don't even have to split it up if you don't want to. You can just basically do this directly, treating your j and k as components, integrating term by term. So if you're able to do this all in your head, you can write this in just a couple of quick steps, basically, right? So that you could start plugging things in and say, okay, when we plug in 1, arctangent of 1 is pi over 4 times 4 is pi. So we have pi j plus the natural log of 1 plus 1 is 2. So we have natural log of 2 times k. Put that in parentheses so that's not confused. So that was evaluated at 1. We could subtract the evaluation at 0, where we get 0j plus natural log of 1k. But again, this is 0. So we have this vector minus that vector, and that is just, again, the vector that we started with there. Or not started with, ended with on the previous thing. So, a lot of things just depend on how comfortable you are with the integration and how messy the integration is, right? These were relatively simple integrals. Most of the integrals in this class shouldn't get too messy. Well, let me rephrase that. Some of the integrals will get messy, but those are usually just kind of, you're doing stuff with polynomials, you'll have a lot of algebra. Most of the integrals you work with in this class should not be too hard. But you do need to make sure that you know the basic integration techniques, right? Know all of your trig integrals, know how to work with integrals of trigonometric expressions, make sure you can do U substitution. There'll be substitutions all over the place. Occasionally integration by parts will show up. You shouldn't really have to do too many of the more advanced techniques like trigonometric substitution, for instance, or some of the more esoteric things. Those should, they may show up on homework from time to time, but you won't really be expected to do too much with those. And especially on a final exam, we don't expect you to remember every single advanced integration technique from Calc 2 or anything. But those common ones, like I said, especially the trigonometric integrals and substitutions, are going to be very important and frequent. So make sure you can work with those. But yeah, a few different ways that you can interpret these integrals of vectors here, depending on whether you want to take it, if it's simple enough and you feel confident enough that you can take it all at once, like I did up here. You can probably do this in just a couple of steps. If you would rather divide and conquer, you can certainly do that. Split the thing up into separate integrals, and you can deal with each integral separately as its own little package, and then just bring things together at the end if you wish.